Great, awesome. Yeah, so welcome. My name is Yixiao Ying. As you can probably see, Recitation will be on a weekly basis on Tuesday, and it'll be Zoom, so you don't have to go anywhere. You don't have to go to classroom. You sit wherever you want, and all you need is a laptop. The recitation is going to be operated as the following. So sometimes the professor could instruct me to give like particular examples. The most likely come from either lecture notes or textbooks, or I don't think I've seen anything from homework yet, but I'm guessing that's also included as well. So that's kind of like the range of problems or topics that we're going to talk about. Specifically for the purpose of recitation is really about not just giving you the answer, but also to train you how to write out a solution. So we're really going to take it slow. We're going to take it step by step, and we're going to make sure everyone follows what's going on. And during the process of, anything that you think maybe you don't remember or maybe you don't know, just let me know, and we can stop and go through those steps. But hopefully this is clear for everyone. Let me see what else. So in case that you want to come back and review the videos, I will post the videos on a YouTube link. I'll tell you guys what that link is by the end of the session, and you can always just check that. It's always it's always on the same channel because it's under your YouTube account. So hopefully it's easy to remember. All right, I think we're good to go. So let me start sharing my screen, and we can start walking through a couple of problems. Sorry, do you have a question? Any questions? Okay. No. Okay. No, let me know if you do. It's okay. Okay. So let me share my screen. Okay. Can everyone see my screen? Give a thumb up if you can see it. Give a thumb up if you can. Good. All right. Awesome. Cool. Let's start. All right, the first problem, it's a standard MLE problem. It's going to be from chapter 7. And I think Professor probably mentioned this, but I want to just emphasize that due to the nature of how we design the courses, probability theory as well as statistical inference, we're trying to break this textbook apart. The first 6 chapters is probability theory, and starting from chapter 7, it's inference, which is why you kind of like start from the middle of the book and you kind of wondering what's going on. So that's what's going on. The problems we're going to start is MLE. So that's going to be the first problem we tackle. So we can start. All right. So let's see. All right. So this is going to be example 7.5.4. And then I will try to write a little bit of what the problem says. So this is sampling from Bernoulli. And this type of problem usually start with a sequence of, ID random variables or sequence of random variables or any kind of wordings like that. So generally, when you see something like this, you can kind of expect that this type of problem is some sort of inference problem that's asking you about MLE, or it could be method of moment, something like that. But we're going to take a look at another example after this. But essentially, we start with x1 to xn, and then it's a random sample from Bernoulli. So generally, we use this kind of wiggle sign that basically just means it's from Bernoulli distribution. Now, Bernoulli distribution, if you remember from probability theory, it has one parameter. It's like kind of like coin toss, right? It has one parameter. So we're going to call that theta. All right. Now, theta, you may or may not know that, right? But what you do know, based on the definition of Bernoulli, is that theta is between 0 and 1. It's a probability. Like the probability cannot be like 200% or like a negative 5%. It's 2%, 3%, 10%. You know, it's between 0 and 1. So what that means is we can say this condition here that theta is really in between 0 and 1. All right. So now you observe a bunch of data, and you know this data, this x, right? It seems is a Bernoulli. Then what that means it's 1 or 0. It's a coin toss, heads or tail. Sometimes I've seen some problems that they don't really tell you that it's 0 and 1. Based on Bernoulli, you kind of have to know that. Okay. So that's kind of like a little caveat that might trick some people, but hopefully that's not the case for you. So 1 or 0. The question might ask you, what is MLE of theta? So question. What is the MLE of theta? Okay, so MLE here is referring to maximum likelihood estimate. And you know, hopefully that definition is clear from the lecture, but if not, let me know. Cool, okay. So the first thing to tackle this type of problem, well, it's the likelihood, right? So the first thing is obviously write out the likelihood function. Okay. Here we have n terms. Right? So what do I mean by that? So here you have x1, 2, 3, 4, all the way to xn. So the likelihood function should be dependent on this n. Right? If n is 2, you have 2 terms. If n is 10, you have 10 terms. If n is n, there are n terms. Right? So here, first is to write out likelihood function. So you can write something like that. And this is defined as a product of a bunch of things. Excuse me, I think one person's in the waiting room. Let me get them in. All right, I think everyone is here. Okay, sorry about that. Okay, yeah, so let's continue. The first thing is about likelihood function. Let's write that out. It's a product of n terms. So that is this capital pi is essentially product I from 1 to n. Inside of this product, we're really looking at either the mass function or the PDF of whatever distribution that we're looking at. Okay, so in this problem, we're looking at Bernoulli. All right, so Bernoulli is a coin toss, right? So then we need to write out that mass function for that coin toss for the Bernoulli random variable or Bernoulli distribution inside of this product. So what that means is theta xi 1 minus theta 1 minus xi. And here we can put a remark. Recall PMF of Bernoulli. All right. Sorry, somebody else in the waiting room. Let me get them in. All right. Anybody have any questions so far? Good. Let me see the chat, make sure that everyone's following. All right. Okay. So for those of you who joined late, right now we're talking about example 7.5.4 from the textbook. And the goal is not just to give you guys the answer, because answers on the book. The goal is to train you guys to write out the solution rigorously, so that in the future or in the exam, and if the problem changes, you guys have the tools to know how to write out detailed answers without getting points taken out. All right, so feel free to interrupt me and let me know if you have questions. All right, so that's likelihood function. This n here is dependent on whatever index that's given in the problem. If the problem has 2, then you have product of 2 terms. And then this I will be from 1 to 2. Here it's a generalized, this is n, so I from 1 to n. All right, so let's continue. Once we have this set up, then we can kind of just do a little bit of, mathematical derivation, right? Like mathematical arrangement. So what I mean is theta. Let me take it really slow, okay? So let me take it really slow by writing it completely out, just like that. That's the first term, I equals to 1, all right? Product means n terms multiply each other, okay? So what that means is we have theta x2, 1 minus theta, 1 minus x2. Make sense? So the first one is I use I equals to 1, I put in here, I put in here. That will give me this first term. And then multiply I equals to 2 coming here, and that becomes this term. Make sense? Right. So there are n of them, right? Because here there's n. So what's happening is I need to continue to write I equals 3, I equals 4, I equals 5, all the way to n. So what that means is this goes to xn, 1 minus theta, 1 minus xn. All right. So what that will give me in the end of the day is theta. Now that's the power term, right? So if you put them together, it's a sum, right? So that's kind of a little nice, and you're gonna see why that's a little nice and makes our lives a little bit more easier. So let's write it out. So that's gonna be sum I xi, and this I is from 1 to n. So that takes care of all these terms, right? So they come in here and become the summation. I have yet need to write out 1 minus theta, and in this 1 minus theta, really you're having all these n terms add up together. So you have like 1 minus x1 plus 1 minus x2 plus 1 minus xn. And you're going to realize that there are n ones, okay? So these guys, if you bring them out, you're going to have an n here, all right? And then you need to take care of these guys. Well, that's just, the sum of x1 to xn, right? But you need to add negative in front of it. So that becomes this. Essentially summation I from 1 to n, xi, but you need to subtract that, all right? So any questions about this? Good? Give a thumb up if you're good. Give a thumb up if you're good. Any questions? All right, awesome. I've seen some thumb ups, so good. We're good. All right, perfect. Now from here, that's our likelihood function. All right, we have a general idea of what's going on. That's the parameters. It's this weird summation of xi, whatever. So what is happening is we want to find like the optimal solution, right? That's our goal. And it usually relates to taking some sort of derivative with respect to theta, and we want to set out to 0 and solve it, okay? So that's the general idea. But here, in order to make our lives easier, I'm going to, use this trick of taking a log so that some terms will actually disappear, and I'll be able to bring this summation term up front instead of staying in a power term. And this is just to make our lives easier in terms of mathematical derivation. All right. So so this next line is really about just taking a log. So I'm just going to call it L theta. Let's just use a textbook notation, and then essentially take a log. To take a log of the likelihood function. And then the rest is math, right? So you expand it. So that's going to be summation I from 1 to n xi log theta plus this power terms comes up here. So that'll give you n minus summation I from 1 to n xi log of 1 minus theta. All right, so that's just taking a log, and log of a product of something is something plus something. A log of something to a power terms, the power terms will come up front to become a constant term in front of it. So that's a basic rule from calculus. Yeah, hopefully that's clear. If not, let me know. So now you kind of see this is maybe a little bit more clear and maybe a little bit more easier in terms of taking derivatives, right? So now the goal is to find the optimal point, and again, we're going to take derivatives. So what we're going to do is the following. So usually you say set the first order partial derivative. So partial theta, because it's with respect to the parameters of interest. Okay, here in the problem, the parameter of interest is theta because the problem asks us to find MLE of theta. That's what we're interested in. All right, so partial theta of what? Of your L theta, the log likelihood function that we just find. All right, and we want to set that to 0 and solve it. Okay, so set this to 0 and solve it. Okay, so generally I like to write this out like this, but of course you can write it out, you know, left to right, right to left, doesn't matter, right? They're equal sign. But generally I tend to write it out like that, and you take derivative, right? So summation, that stays the same because that's a constant term. It has nothing to do with theta, right? Log of theta, the derivative of log of theta is 1 over theta, right? So let's write a remark. Partial theta of log theta is 1 over theta. So we say recall. And if that's the case, then this 1 over theta comes up front, right? And what we have left is, I am running out of space here. All right, so sorry about that. All right, so now the next term is, let's continue. It's going to be n minus summation I from 1 to n xi. And then we have 1 over 1 minus theta. All right. All right. So, you know, obviously you can write 0 prompt, but if you don't, it's perfectly fine. And then I'm making a small error here. I don't know if you guys can spot it. This is actually not my plus. This is actually minus. And the reason this is minus is, you know, because we have this minus sign here. It's like a chain rule, right? And this is kind of nice because this actually gives us, let me move this up from here a little bit so I can give myself some more room. This actually becomes just theta summation equal to 1 over 1 minus theta n minus summation I from 1 to n xi and close the parentheses. All right, so I'm not really doing anything strange. I'm just moving this term here, right? Just moving one term to the left-hand side. Now I'm left with nothing but to actually solve it, right? So how you do that? So you essentially rearrange a little bit. So this 1 minus theta come over here. That's a summation. And then on the right-hand side, you have n theta minus theta summation I from 1 to n xi. Okay. So we have these terms here in the bottom of the fraction. So all I'm doing is I'm multiplying the theta 1 minus theta on both sides, so I can cancel out the bottom of the fraction, and that's it, right? And on the right hand side, since we're multiplying theta over here, you just distribute theta inside here and then inside here. That'll give you n theta and theta summation xi. All right. And then something magical is going to happen, because if you realize that this is theta summation, this is theta summation, so these two terms actually cancel out. All right, so let me erase this and just write it as, let's see. So we have summation, let me just make sure everyone can see this, minus theta summation I from n xi, right? That's the left-hand side, right? So now if that's clear, let me get rid of that. Then I can move this here. All right. Now, as I said, something magical is going to happen. This is going to cancel out. This is going to cancel out. And you're left with summation I from 1 to n xi equal to n theta. And the theta, to solve for theta, which is the MLE, the maximum likelihood estimator, will be the result of this equation. All right, so theta hat is going to be 1 over n summation I to n xi, which essentially just x bar. Make sense? All right. Any questions about what I just said from beginning to the end? Good? Give a thumb up if you're good. All right, awesome. I see one thumb up. I'm gonna assume that this is okay. Oh, by the way, for those who joined late, this is recorded, and I'll tell you guys a link in the end of this presentation. So if you miss anything, you can also go to the YouTube and review the video. Okay, so let me take a look at my notes. I think the next problem I want to talk about is in the lecture notes. I think it's a method of moment problem, so we can go to that as well. The calculation is actually pretty straightforward, but let's just go through this, just make sure that everyone's on the same page. Okay, so this next one, it's going to be example 2.5. And this is from notes. Cool, okay. Same setup, right? X1 to Xn from normal mu sigma, right? Same setup. So let's write that out. X1, X2, Xn come from normal mu sigma square. Oh, by the way, I've actually seen some people write this. This makes no sense in the environment of our department, right? So because we refer to mu variance, so the two parameters in normal distribution, it's mean and variance. It's not mean and standard deviation, right? So if you write this, they can actually think that sigma is the variance. And then standard deviation is like square root of sigma, all right? So to avoid confusion, the first one is always mean. The second one is always variance. Okay, so that's just small caveat. Sometimes the problems could trick you though. Sometimes the problem could just write like this. But you're gonna have to know that's variance. Now, hopefully, in this course, they don't do that to you guys, but I've actually had problems like that before, and I actually made a mistake on that. So just a small caveat, notation-wise. If it's unclear, ask. Right? Ask in the exam, ask the TA, whatever, ask. Okay, so let's continue. That's setup, right? That's the data, the compound normal distribution, mean variance, right? That's a setup. And there's a parameter set, as we discussed. This parameter set, they call it theta, which essentially just a set of mu and variance, mean and variance. So let's write that out. That's your mean, and that's your variance. All right. Okay, then the question asks, what is the method moment estimator? So question, what is MOM estimate? MOM is short for a method of moment. So that you can just directly write it in your exam. No one's going to question that. Okay, so you guys know the basic setup of how to calculate the method of moment. I'm not going to bore you guys with that, go into that. I'll just write out the equation, and there's some derivation. I don't think it's horribly hard. But essentially, the first thing to realize is well, mean and variance, right? So whenever it comes to this kind of problem, you kind of ask yourself, hey, you know, here's a normal distribution. What is your expectation? You know, what is your expectation x squared, right? That's kind of like how you get started. So so let's start writing down. So okay, so because we have our data come from normal mu sigma square, then expectation of x, you can say x1, it's perfectly fine because you know, they're like independent, right? Like it's kind of like one, just like notation wise, you can say expression of x, you can say expression of x1, each are fine, but let's just stay with the textbook notation. So expression of x1, and that's mu. Nothing else will say. It's a mean, right? And the second one, well, the second one, do a little bit of calculation. So the variance of x1 is sigma square, and what is that? That is expectation of x1 square minus parenthesis x expectation of x1 parenthesis square. And we know that the second term, right, this guy is mu square, right? So you write mu square, and what does that give you? That gives you expectation of x1 square is sigma square minus plus mu square, right? All right, so that's like your first moment and your second moment. Okay, and if you miss the definition of moment, you know, let me know. I think all that's covered in probability theory. But yeah, if that's unclear, let me know. Okay, so that's a setup. All right, that's a setup. And generally, people write this as mu1 and this as mu2 to simply just illustrate the first moment and second moment. All right, so that's your setup, right? So you can kind of think of that as like a two lines of equations, like two equation, two unknown, right? So recall two equation, two unknown. All right, so if it helps, you can kind of think like this. All right, so now you're left with nothing but to just solve it, right? So how do you solve it? Well, that's your one equation, that's your two equation. So from one, you can directly write out the answer, right? It's just, you know, one line, A equals to B. So that's clear. Then from one, you can plug in mu to essentially the next term, right? So you know, so your sigma square plus mu square equals to mu2. Now, if you plug that in, you're just gonna have mu2 equals sigma square plus mu square. All right, so let's see. let me just double check a little bit of all right, so yeah, so you can just plug in. So plug 1 into to get mu2 is sigma hat plus mu square. All right. Let's see. Any questions about this part? We're going to take a look at another method moment problem. So hopefully that's a little bit more clear because that requires a little bit more derivation. This one kind of just like you solve it and that's it. All right, so if there's no question, let's continue to look at another problem. Okay, so next problem is going to be, let's see, next problem is going to be 2.6. So let's write that out. This is 2.6, and again, this is from the notes. Okay, so same setup. We're going to start with n, a sequence of n random numbers from gamma. So x1, x2, all the way to xn, and this is from gamma. Now, gamma distribution has two parameters, right? Alpha and beta, right? And from probability theory, hopefully you remember how to find expectation and expectation square. So you know variance. And here you can just directly write it out, right? This is inference class. We're not going to test you guys on how to find expectation, all right? So this kind of stuff, if you don't remember, you can write it on cheat sheet. I'm actually not sure if they're going to give you cheat sheet from previous classes. Usually they do, but if not, then you might have to memorize it. So recall expectation of x. This is if x is gamma, all right? It's alpha over beta, okay? And the variance of x is alpha over beta square. We do the same trick that we did for normal distribution. So what that means is we have expectation x1 square minus expectation x1 parenthesis square. And the second guy is alpha over beta square, right? So what that means is expectation x1 square is going to be alpha over beta plus alpha square, excuse me, there's a square here, over beta square. And thus we have expectation of x squared, that's going to be alpha plus 1, oops, sorry, over beta squared. All right, we're good. Any questions about this? Give a thumb up if you're following. All right, awesome. Okay, so those are your two equations, right? Two equations, two unknowns, right? Those are your two equations. So you write it out, you can say something like, okay, so alpha over beta, that's your first moment, right? So mu1. And then also you have your second moment. So alpha plus 1 over beta squared, so mu2, right? Two equation, two unknown, okay? That's 1, that's 2. So now we're gonna solve it, right? So from equation 1, what do we know? Alpha beta, you move one to the other, right? So alpha equals beta times mu1, right? And then we use that, plug that into equation 2, and then we solve for beta, right? So plug alpha equals to beta mu1 into 2. Okay, so what is 2? 2 is this weird alpha plus 1 stuff, right? We're gonna plug things in. So what do we have? This, I'm gonna write this as alpha plus 1 equals to beta square mu2. All right, so left hand side, I have this, but then since I'm replacing alpha with beta mu1, okay, so I'm gonna have beta mu1, right, square plus beta mu1 equal to beta square mu2. All right. So now, if I recall correctly, there is a condition that alpha beta greater than 0. Right. So let's highlight that. Because of this, it allows me to cancel out one of the beta terms. So that's gone, that's gone, that's gone. All right. So what that gives me is beta mu1 square plus mu1 equals to beta mu2. All right. So because in the condition, we know that beta can be 0, right? So I can divide both sides by beta, kick one out, and make my life easier. All right, so we're almost there. Now you just solve for beta, right? So these terms I can move here and I can factor beta out. That's gonna give me beta mu1 square minus mu2. And then on the right hand side, I have negative mu1. And my beta hat is going to be mu1 over mu2 minus mu1 squared. I have a minus here, so I replace the order. So cancel out this minus. So that's why we have that as our final answer for beta. Since we're solving as a solution, so in the end, you can write beta hat. This is going to be indicating that this is a solution for beta, not like beta itself. It's a solution, you know. So it's a beta hat. Okay, so I think we're halfway home. You know, we have our beta hat, right? Now all you gotta do is figure out what alpha is, and then we're kind of done, all right? So now with that being said, we can essentially plug beta hat in here. So this is beta hat, plug that in essentially equation 1. So what is equation 1? Well, equation 1 is up here, right? So you plug in beta, then you can solve for this alpha term. So that's the story. All right, and then you just say alpha hat is, you know, beta times mu. So beta is this weird thing. So let's write that out. Mu1 over mu2 minus mu1 squared times what are we timing? Times mu1. And this will give you mu1 squared over mu2 minus mu1 squared. All right. Okay, so that is going to be the method of moments estimator for gamma distribution in this problem. All right, so let's pause. Any questions? Questions? Good. All right. Okay, so yeah, so let me know if you have questions. Let me just mention a small caveat. I don't think it's mentioned in the book. Let's see. All right, I think it's here. So I don't know how many of you are taking machine learning or advanced machine learning. One of these courses to talk about neural networks, right? And in neural networks, there's this loss function called cross-entropy, right, or binary cross-entropy. So that is actually come from MLE of Bernoulli distribution. All right, so I'm going to repeat that again. In deep learning, in neural networks, one of the building blocks is loss function. All right. From machine learning, they're going to start you guys with the basic loss function of mean square error. And the reason they do that is because that is tied up to linear regression. But if you have a two-class classification problem, then you need to use cross-entropy or binary cross-entropy as your loss function. And that comes exactly from this equation. So I'll put a remark. Let me not say recall, that's the wrong word. Let me say this is related to binary cross entropy loss function in neural networks. Right? The reason I'm mentioning this is because when I first learned this concept of MLE, I have no idea where it's used, and I have no idea why this is important. And it was like 2 years later, I learned neural networks, and I finally realized, okay, this stuff is important. Okay. And in machine learning, you can kind of think of this theta as your estimate, and that x is your target variable. So usually you use y, right? So you have something like a y hat y kind of thing. I'm not going to bore you guys with that. That's going on tangent of this course. But just a small caveat to help you guys memorize why this is important. All right. So let me pause. Any questions about what I just said, about these examples, MLE or a method moment? Any questions? Let me double check.
A question.
Yes.
Yeah. So you just mentioned cross-entropy is a loss function, and I am wondering what is the difference between a loss function and a MLE? So because when we're doing loss functions, we're trying to minimize it, right? But here is the maximum likelihood. So I think it is like we are going to maximum the likelihood function. So what is the difference between them?
Yeah, that's a good question. So the difference is, let me tell you what's the same. The same is a setup. The difference is the goal. Okay. So if you have, let's say this, I will make a new page and I will show you what that means. So let's say, so the same, let me talk about same thing first. The same is the setup. So both require likelihood function. Now the difference is in MLE, we're solving it, we're treating this as a simple, how do I say, because the log is monotone, right? The log function is monotone. So we're simply trying to find the optimal point in that function, and that's it. But in loss function, that's the setup. That doesn't entail you, it doesn't tell you anything about how to solve the optimization problem. Okay, so let me write that down. In MLE, logarithm is monotone. We find the best point, right? We find the optimal point. MLE is the optimal point. Done. That's it. You find the optimal point. That's your MLE. That's the answer. End of the question. In machine learning, you have the loss function. It doesn't tell you what to do next by itself. Loss function by itself just tells you, here's your target, here's your prediction, how many mistakes you're making. Okay, so in loss function, if I choose cross entropy, suppose, so assume two class classification. So making these two assumptions, I can then write out the cross entropy. So that will be, let me make sure I have one more assumption. So suppose y hat is prediction of y. All right. So let me make sure that's very clear. So now this loss function can be written as summation I from 1 to n. You have your let's mimic what we're writing up here. So it's this line. Right. I'm copying this on purpose because I want to mimic what we just talked about. All right, so recall. Right, so now what do we have? So now we have our yi log y hat I plus and then plus, well, this is inside of summation. So I'm going to write 1 minus yi log 1 minus yi hat, right? So now I can erase this. All right, so this is binary cross entropy. All right, so loss function by itself just tells you this is your y, this is your target, this is your prediction, how many mistakes are you making, how different they are, right? It doesn't strictly tell you how to find the best solution. Not yet, right? Not yet. At least not from this line of equation. Not yet. We don't know that. What you should keep going is using some sort of gradient descent optimization problem. So now, we're not going to talk about details, but I'm just going to give you a just to answer your question. Then you use gradient descent to solve this optimization problem. All right, so let's draw a line. What's the difference? That's the difference.
Okay, that makes sense. Thank you.
Yeah. Great. Awesome. That's a good question. Any other questions about what we just talked about? Okay, good. We have a few minutes left. I think Professor also instructed me to talk about 2.7, but I think 2.7 is actually very similar to normal distribution. It's really just like one line of solution. You write out the first moment, you write out the second moment, and you solve it. Yeah, I don't think you guys have any problems. If you understand, if you can understand gamma, you're not gonna, miscalculate a Bernoulli unless you're like drunk or something. But other than that, I think you're good to go. All right, so yeah, so I'm gonna stay a few more minutes. Ask me any questions you like, and if not, then you're free to go.
Hi, can I ask a question in homework? And I guess it's from chapter 1. Is it okay?
Chapter, oh, you mean chapter 1 of the book?
Yeah, no, it's the lecture notes. It's about asymptotic distributions.
Sure, yeah, sure.
So it is from 6.3.14. It is a homework question in the textbook. So
Let me find, sorry, give me one second, let me find it. 6 point,
3.14.
6.14.
6.3.14.
6.3.14. Give me one sec. 6.3.14. Okay. Oh, I think I found it. Okay. So what's your question?
Yeah. So the question says that the x1 to xn are random norm vectors from normal distribution with mean 0 and unknown variance sigma squared. So so in this section, I am assuming that I let yi equals to xi squared, but I mean, I am talking this to my classmates, and we have different solutions to this question because I think that we should let yi equals to xi squared, but my friends think that this yi should be equals to the summation of xi squared. So in my solutions, if I let yi equals to xi squared, and then I can calculate the like the sample mean of yi, which is 1 over n and the summation of xi squared. So I mean, I have a question is that what should I set yi to? Is it, should I set it to xi squared or the summation of xi squared? I'm not sure.
Yeah, okay, so yeah, I heard your concern. Okay, so first let me say that there isn't really one fixed solution as long as your derivation is correct. So keep that in mind.
Okay.
So yeah, so I care more about the derivation than what you set to, but based on what you're describing, if you have like if yi is xi squared versus, or if y is like summation of xi squared, then I think you probably just the solution should be difference by like a factor of n, something like that. Or like a function of n. I'm not sure. I have to take a look at the solution first. But I think to be honest, there isn't really a fixed answer. What you do have to realize is there's two parts, right? Part A and part B. Part A, it's asymptotic, so if you leave a n in the variance, no problem at all. But part B, you have to kill that n from the variance, otherwise it will deplete as n goes large.
Yeah, and so in the lectures, the professor give us a example about like it is quite similar to this question. It's also calculating the simple distribution of it is x and bar, which is the sample mean of xi's. So the xi's in the lecture is from the normal distribution, and zero mean is 0 and variance is sigma squared. So in the lecture, the professor gives us an example which use the central limit theory, which is he's using the sample mean of xn, which is squared n times xn bar minus mu, and that is converges to distribution to normal distribution of mean 0 and variance sigma squared. So I mean, in a homework question, I am trying to mimic this solution to calculate the yi square, yi bar, which is the reason why I set yi equals to xi squared rather than the summation of xi squared, because I would like to calculate the yi bar. So when I set yi equals to xi squared, I can calculate yi bar into 1 over n times the summation of xi squared. So that is my thought.
I think if your derivation is correct, I'm actually a little confused of if you set yi equals xi squared, won't you get like a, because then you're gonna have like a let me think about this.
If I set yi equals to xi squared, then I am trying to calculate the asymptotic distribution of yi bar, which is 1 over n and the summation of xi squared. So and that is the one that the homework wants us to calculate, but it is like 1 over that. So
I see what you're saying. Let's see. Let me open up a new page. All right, let's see. If you have what distribution is normal mean 0 variance. Okay, so let's say this is mean sigma squared, and then let's see, you have that's your central limit theorem -0. Well, that goes away, so this is goes to normal 0, 1. And if you substitute, so let's see what you're doing here. So this is actually, so if I want to expand that, it's actually just this part to nxi, and then that is normal 0, 1. But if you,
I guess it's normal 0 sigma squared.
oh yeah, you're right. Sorry about that. It's normal 0 sigma squared. And then so you are trying to substitute, so you let y equals to yi equals xi squared. Is that what you're trying to do?
Yeah.
Isn't the math going to be more complicated if you do that way? Did you use the fact that this is going to be sigma, and this is going to be 2 sigma 4?
Yeah.
So you use these two, and you use the delta method?
Yeah.
So what's your final answer?
Final answer. Well, I guess I have calculated the EXI4 wrong. So maybe my final answer is wrong, but I'm just trying to figure out is this way right or wrong to set yi equals to xi squared. Because I have talked to my classmates and they have said yi equals to the summation of xi squared, but I just don't get it.
I think you're better off setting yi to the summation, and the reason is because you want to set this up as so you want to set it up such that you can use delta method. Does that kind of, oh sorry, I think someone's in the waiting room, I don't know why. You want to set it up so that you can use delta method. Does that kind of make sense? Let me just write a little bit more so that we're clear what's going on. Right, so I think what you want to do is something like this. You let y equals to let me use the correct notation. N equals to summation I from 1 to n x square. You can even set like this. I don't know if your friend did that, but this is the easiest way to solve it. When I say easy, I mean like less lines. Okay, and so first of all, you need to realize that this, so let y equals this, then yn has asymptotic mean sigma square and variance 1 over n. I think there's a 2 somewhere here, 2 sigma fourth. So that's kind of like the like step 1, you know. And then it kind of gets easier. You just use delta method.
Got it. So here that yn also is a normal distribution of mean sigma squared and variance 1 over n to sigma 4. So here the yn.
Yeah.
Okay, got it.
Yeah. So the reason you do this is because the question asks you, right? The question says in part A, it asks you the asymptotic distribution of the statistic, right? So something like this, right? That's what the question asks you. It's a square or whatever, right? And then immediately you realize, okay, I don't like this -1. It's kind of like mess everything up. Right? I don't like that. So what I'm gonna do is I'm gonna cook up everything in the middle of the parentheses and make my life easier. Okay, so don't just try to mimic the steps in a lecture. I'm not saying that's wrong. I'm saying you wanna think outside the box a little bit.
Okay.
Yeah. So you wanna ask yourself what makes your life easier. Well, what makes my life easier is I can use delta. Somewhere down the road, I wanna say by delta method, I can do something. Well, how do I do that? Well, I need a G prime. If there's a G somewhere here, I need a G prime. So what makes my life easier? Well, if this is X inverse, then I know exactly what G prime is, right? You know, you take something like that, right? I know exactly what G prime is, and then great, then I can use delta method.
Okay, got it.
Yeah.
Thank you so much.
Yeah. Then you know, then you can't get what's going on. Okay, so how do I make sure that I have this? So how do I make sure that I have this guy here? Well, if I can somehow magically cook up this X to look like this, then I'm done. Then everything in the middle, everything from here, everything in this area should be how to get to that, how to make your yn look like this guy. Like look at this guy here. Yeah.
Got it. Yeah, thank you so much.
Yeah, of course. Yeah, no problem.
Hi, I had like a question in this. Firstly, like how do we just ignore inverse? Like why are we just ignoring inverse in this case?
It's not about ignoring inverse. I would say it's more about knowing that inverse is not something that you can like directly compute. You have to use delta method. All right.
Yeah.
So when I see inverse, immediately in my mind, I know I have to use delta method.
Okay.
So that's the first key point you have to realize. And unfortunately, that either come from either memory or come from experience of working out problems. And that's okay. If you don't have it, that's completely fine. I'm telling you right now that when you see inverse, it's something that you realize you need to use delta method. Okay. So because in the parentheses of inverse, you have all these weird summation, blah blah blah, and delta method doesn't really give you that. Because why? Because delta method requires your function to be essentially monotonic. Make sense?
Okay.
So don't just memorize delta method. Memorize the condition of delta method. That will help you a lot when you're solving problems.
Okay.
Okay. So you follow. So okay. So let's erase this. Okay. So I'll tell you the thought process, because answers are online and you can find the answer. But the thought process is extremely important. So when I see something like this, okay, the first thing I realize is I need this guy and then I need this guy. As two things. Oh, sorry, not square. This inverse. Two things, right? Two things. First thing come from some sort of derivation or some sort of manipulation of your x, such that you can come up with, you can use chi-square, or you can calculate it from scratch, or you do whatever you want, right? And you get straightly from x1 xn all the way to essentially the sample mean of xi square. So this is kind of like a sample mean of that, right? Which is why earlier the student asked, okay, then why don't I just do this? That makes my life easier, right? That's kind of how she's thinking about it.
Yeah.
Right. So you can do that, but I think the math is actually going to be much longer if you work it out step by step. I think you're better off just setting the whole thing up as y, and you're better off just setting up this whole thing as y. That'll make your math much easier. So that's the first step. And then second step is great. I have everything in the middle of parentheses. Let's use delta method. So then delta method, you set, or generally people say let g of x to be exactly what this is, right? This inverse tells me what should I put in this g of x. If this is -2, then I should write x -2. All right. So that's exactly what I need to do here. Thus, g prime is going to be that.
Oh.
Then you can use the delta method, right? So if you have so here if this this is technically speaking yn. So if this yn has asymptotic mean of what was the thing I just wrote down? Asymptotic mean of sigma square and variance of this is weird, something like this, right? Yeah. Then I have a central limit theorem, and I have the delta method. Then I know exactly what is distribution of this thing, right? So what I mean by that is I can move this down here, and I can say something like yn converge to you can probably expand. Oops, you can probably expand this a little bit. Normal 0, this guy. And then if you want to be non-depleting variance, right? Non-vanishing variance, then you can move this n to left-hand side. So what I'm going to do is I'm going to erase that and become square root of n. Right. So now we can talk about using delta method. Right. So what do I mean by that is
over here the mean is not 0 and it's sigma square, right?
I wrote it here.
No, on the right. Because like a corresponding mean we had just found out has asymptotically mean of sigma square.
Oh, wait a sec. Let me see. If I move it here, it should be a sigma square. Is that your question, or?
No. So it tends to normal distribution of, would it be 0 and 2 sigma 4, or is it sigma square and 2 sigma 4 by n?
Let's see. You have let's say you have an x bar has so expectation of x bar is 0, and your I'm sorry.
Yeah. Okay.
And no, basically what I'm trying to say is you have your x bar. So what is asymptotic distribution of x bar? You use central limit theorem, right?
Yeah.
And if I write this minus let's make this a different number. Let's say this is mu, right? So you have x bar minus, if x bar has asymptotic distribution, asymptotic mean of 0 and variance of sigma square, well, asymptotic then it's over n, right? Then what do you write? You write something like this. You can do this, and this is mu, and this is normal 0 sigma square. Make sense?
Yes.
So why do you need a mu here?
Okay, yeah. I mean, so whenever after even doing the delta method, only our variance changes, but like our mu remains the same. So that is why over here, like below, it tended to normal distribution of 0, 2 sigma, 2 by 6 into sigma to the power 4, right?
Yeah, yeah.
Okay. I also had a doubt on 6.3.15.
6.3.15.
Right.
Oh, okay. I have it here. Okay. What's your question?
Like I don't. How do I start it? I didn't like understand. I mean, how do I formulate the?
Let's see. X1 to be a sequence of ID random variables, each having the uniform distribution on the interval for some real number theta. For each n, define yn to be the maximum of x1 to xn. Wait, what's the question? Oh, next page. Okay, so part A, show that CDF of yn is f of n y over theta. Okay, and then part B, show the convergent distribution. Okay, what is your question exactly? Like how to get started or something?
Yeah, how do I mean, start it or like formulate this?
Let me see if I can give you a hint. It seems like to me part A is like kind of like probability theory stuff. I wonder why they ask it here. All right, so it goes something like this. Let's see. I'm trying to give you a hint without giving you the answer. Okay, so all right, let me just write something down first. So first of all, you have essentially, that's your data, right? You observe a bunch of x1, x2s and their ID, and then they fall on uniform. So it goes something like this, and then the support of that is 0 theta. So something like this. All right, and now for each n, define yn to be the maximum of like x1 to xn. So imagine yourself a graph like that. And let me make sure this is so the 0 theta. So unfortunately, I'm gonna have to call that 0. I'm gonna have to call that theta. So that's 0. That's theta, and that's gonna be your line from 0 theta, and then that's your function, right? So kind of like straight line because it's uniform. So whatever this x1 to xn is, the largest of those is going to be your yn, right? So you're gonna have a bunch of dots. Like you're gonna have like, let me see if I can draw something. Like imagine you have like bunch of dots here, and then somewhere here doesn't have to be exactly theta, but very close to theta. So somewhere there is this maximum of xn, oh, sorry. The max of x1, x2, xn, we denote that as your y or yn, denote that as your yn. So you can kind of think of this as, well, then if I give you a small sample size, then maybe it's going to be something like this. Like, let's say I give you a small sample size. Then technically speaking, that's your yn, right? Let me use a highlight. So if that's your sample size, just 3 dots, right? Just 3 dots. Then this guy is going to be your yn. Okay.
Yeah.
What is the chance that happens? It's whatever this is divided by theta, right?
Yes.
Good. If you can get that, that's perfect. Now, if you resample it, and maybe you have 4 dots, like something like this, then that's going to be your yn. So what is the chance that happens? What's the probability that happens? It's whatever this divided by theta, right?
Yeah.
Exactly. So now you kind of get the point. You kind of get an understanding of what the probability looks like.
Yes.
Does that kind of make sense?
Yeah, it makes sense, but like, how are we proving that this is like the CDF by that? Because I think we have to prove that it's
Oh, I see what you're saying. So mathematically, you want to set it up as so okay. So you have your right hand side, right? Because the problem tells you show CDF is whatever that is, right? The FNY blah blah blah. So now you want to set up to be probability yn less equal to y. So this is the definition of CDF, and this is going to be now here's a trick. Yn is the largest among all the x, all right? So what that means is, and since all the x are independent, so I can write this as x1 less than equals to y n times. Does this make sense?
would it be x1 less than equal to y, or would it be xi less than equal to y?
It doesn't matter.
Okay.
I can be 1, 2, 3, 4. Their ID, so it doesn't matter.
Okay. Yeah.
So if you want to write it out, you can think of like this. This is equivalent to probability x1 less than equals to y times probability x2 less than equals to y times probability x3 less than equals to y xn less than equals to y. Because if the maximum number is less than this y, what that means is all of the x is less than y. Make sense?
Yeah.
All right, perfect. So if this makes sense, and also the ID, right? The ID. So I can write it simply as this to the power of n. Does this make sense?
Yeah, it makes sense.
All right, and then you're kind of done.
Okay.
Yeah.
So like, do we also have to do this for a minimum case, or is y hat always like the maximum?
What? No. It tells us it's the maximum. In a problem, it denotes that. So this
Oh yeah, sorry.
The problem told us.
Yeah. It has. I'm sorry, I got confused in the example 3.9.6 that they referred. So over here, and like, okay, y by theta. Okay, so now, right now over here, basically it's y by theta n because of the logic that you had told that so that is why it becomes y by theta to the power n from 0 to theta because of the logic that you had told previously.
Correct. Yes. So
Okay.
if you really want to write it out, you can even add one more line. So let me move this down here. So this is actually exactly probability. Well, yn, the problem tells us it's the maximum of everything together, all of the x, right?
Mhm.
So this is technically speaking max x1, x2, xn.
Yeah.
Make sense?
Yes, it does.
Because the problem tells us yn is the largest, is the largest x.
Okay. And for the part B,
For part B, okay. So part B, let me see. Show that Zn equals to N minus theta converges in distribution to the distribution with CDF. Okay, what is your question exactly?
show that Zn converges in distribution to the distribution with CDF. So over here also, will we be using something like a delta to prove it, the delta method?
You don't have to use delta here.
Okay, because it does not have an inverse.
Yeah, let me see. No, it has nothing to do with it. It doesn't have to be inverse to use delta.
Okay.
Any monotonic function you can use delta. I'm just not seeing. Let me take a look at the problem. I don't think delta is the right way here. The reason is it's not. I can't guarantee that this this definition of Zn, whatever it's like Yn minus theta, I can't guarantee that's monotone, So I don't think delta is a valid approach here. So the right way to do it is you have to go back to the definition. So it's asking you something converges to CDF. So you then need to ask yourself, okay, exactly what is the CDF of Zn? So that's the starting point of this problem. So you need to ask yourself, what is Zn less than or equal to Z? Okay, and obviously, if you want to make it rigorous, you have to say for Z positive. It has to be. It's a CDF. The CDF can be like it doesn't have like -5%, right? It's a CDF. It's a probability. So so that's going to be the starting point, and then you need to ask yourself, how can I rewrite this into something else? So how can I rewrite this into something else that already have the answer? Basically, what I'm trying to say is, the problem tells us what? Problem tells us Zn is N minus theta. The problem tells us this, right? That's definition. Right? So we have to use it. So how do we use it? Well, it tells us this. So why don't we just plug it in? Does that make sense? So
Yeah.
if you plug in whatever this is, you're gonna get this guy, right?
N minus theta.
Good?
Yes.
You follow?
Yeah.
Okay, so if you're following that, then I can open this up. And then I can rewrite this into a function of yn. And I know what function yn is because part A, we already show, whatever yn is, it follows that f and y distribution. We know that, right? So now all I gotta do is I divided both sides by n, so I get something like this. And then I move my theta to the right-hand side. Right, it looks like that. Now I have everything I need, right? Because this is yn, and I know what yn is because from part A, the f of what is it? Y is y
by
over
theta,
theta. Yeah, you got it.
the power
Oh,
n.
of n. Yeah, yeah, you
Yeah.
got it. Yeah. And this is make sure the range is you have the range, right?
Okay. Yeah.
Something like this. And this is a 1 if y greater or equals to theta. All right. So now I can just now this is asking what is essentially what is a CDF of this guy. Well, I have a CDF, right?
Hmm.
Then I can just plug it in. Make sense?
I think they're asking find the CDF of ZNO.
It is. It is. Zn is here. Equal.
Mm. But doesn't this come in terms of y then? Like I think
It comes in terms of y. No. It comes in terms of z. And technically speaking theta, but z.
okay. So basically now we'll just do everything in terms of z, and then we'll basically get the distribution of z, right? I think.
Yeah, because your CDF of z right
Hmm.
now we already did all the work and rewrote it as yn equal to something, like yn is less than equal to something. So basically what I'm trying to say, what we're trying to establish here is the CDF of Zn can actually be written as CDF of Yn.
Hmm.
Okay.
Yeah.
So notice that the input here it's still Z. There's no Y in the input.
Okay.
So we're borrowing what we know from Yn, but we're plugging in a function of Z.
Yeah.
And that gives us the CDF of Zn.
Okay. This last point I'm not that clear with.
Where is not clear?
Basically, like, I mean, this is in terms of, I mean, right now, if we even import y and stuff, so it would come in terms of y by theta to the power n. But like, how do we take out like the z part of it, the fz from this? Because it's in terms of y, right?
The FZ is exactly this, right?
Yeah. Okay. So basically, in the end, z will come in terms of y. Because if we like, 1 second, I'll just look into it. I
Wait.
think
No,
I'm
there's
getting
no Y. There's no Y.
there's no y.
In the beginning, we have a function of Z.
Yeah.
We rewrite it into a function of Yn, but the Yn less than equal to, but the input here, this variable here, the value that this random variable Yn can take from a support, it's a function of Z. There's no Y.
Okay. Okay. Oh, okay.
Yeah, so if I keep writing it out, it's going to be a function of something like this. It's going to be a function of this.
Okay. Okay, so basically what will happen if we like take function of y and is less than function of z, and in function of y we'll just import this value on the right, right?
Yeah, you can do that.
Oh.
Yeah.
Okay. And in the next question that was there, which is 1 second. In 6.5.2, basically they have asked us, 1 second, I'll just go to that question. Yeah. Yeah. So over here we have to explain why x minus lambda converges in distribution to a random variable having standard normal distribution. So in that, what I have done is I showed like the convergence of MGF of Poisson to the MGF of the normal distribution. And then I said that basically because of there is a convergence in MGF, there is a convergence in distributions. So
Wait, sorry, your question is 6.5.2.
yes.
Suppose that X has a Poisson with a very large mean lambda. Explain why the distribution of X can be approximated by the normal distribution with mean lambda and variance lambda. In other words, explain why this converge to random variable having standard normal distribution. Okay. I wonder why they asked you to explain. You just, I mean,
Yeah,
you
it's a lot
prove
of
it. Sounds
derivation.
like, looks like a proof to me, but
Yeah. So I mean, what I have done is I have just done like a the convergence of derivation of MGF of Poisson converges to the MGF of normal distribution, and because the MGFs are converging, I have said that the distributions are also converging. Does that like that's what we have to do over here, right?
I thought you need to use some sort of central limit theorem. Have you mentioned that, or?
I haven't done it through central limit theorem. I have done it through like the convergence of MGF.
Oh, convergence MGF. I think that could also work as well. Yeah, I think that could work. Yeah, I think that could work. Let me take a look at because in my head it looks like a proof to me, but then they said explain. So I'm guessing you can just use English to write it out how you think about it. You don't have to actually prove it.
Okay.
So yeah, so I think as long as you argue how you can use the convergence of MGF, I think that should be fine.
Okay.
You look at write down the MGF standard normal, and you show how MGF of X can potentially converge to that, and then I think you're done. I think that's the answer.
Oh, okay.
Yeah. It doesn't have to be rigorous. I don't think that's what they're trying to do here. You can just simply use English, just write out. Use English to write out. You don't have to derive a bunch of things.
Actually, I just did a 2-page derivation, but like I'll convert it into.
Yeah, if they ask you for derivation, they're supposed to say show this converge to this, or prove this converge to this. If they just say explain why this is this, then you don't have to. Yeah, it's kind of like you write a paragraph in English and then you say like a thought process.
Okay. Sure. Thank you so much.
Yeah, of course. Now I can stop sharing my screen, and good luck with everything. Let me know for questions. Send me an email. I'm happy to help. Yeah.
Thank you. So the recording will be present like on the site, right?
Yeah, I will post on YouTube, and I'll give the link to Professor, and I think he will announce in the coursework.
Oh, okay.
Yeah.
Thank you so much.
Yeah, of course. You got it.
Thank you. Bye. Have a nice day.
Bye. Take care.